Welcome back, everybody, for another deep dive.
Mhm.
This time we're going to be tackling a topic that I've always found incredibly fascinating, a little bit intimidating, honestly.
Yeah,
Quantum physics.
it's one of those things
That's
that
all.
everybody's heard of,
Yeah,
but not a lot of people know a lot about.
exactly. And I think it's easy to kind of just put it in this box of, well, that's something theoretical that scientists are working on.
Right.
It doesn't really affect my daily life.
Yeah.
Um, and we're going to be looking at a no-VA PBS documentary called Decoding the Universe, Quantum, that really, I think, drives home the point that this stuff is not just happening in labs somewhere.
Right.
This is the backbone of so much of our lives.
Absolutely.
So I'm really excited to get into this with you today.
Yeah, this is going to be a fun one.
Okay, so this documentary covers a lot of ground. We've
Yeah.
got black holes. We've got lasers. We've got the nature of time itself.
Yeah.
Where do we even begin?
Well, you mentioned black holes, and those are always a crowd pleaser. And I think it's really interesting that, there was a time when these were pretty much purely theoretical concepts.
Yeah.
Even Einstein wasn't entirely convinced that they were real.
Yeah, and now we know that they're out there
Oh, yeah.
gobbling up stars and planets and
Devouring planets.
yeah, and each other.
Stars.
The documentary even talked about how the first black hole was discovered back in 1971
With an X-ray telescope.
using an X-ray telescope.
Yeah, the X-ray telescope.
Found it lurking in the constellation Cygnus.
Yeah, that was the first confirmation. But you know what's really cool is how much our understanding of black holes has continued to evolve.
Right.
Like Stephen Hawking, for example.
Okay.
He proposed this idea
Yeah.
that black holes aren't entirely one-way streets.
Okay, that's the part with the antiparticle pairs?
Exactly.
Right.
That's it. So picture this. Right at the edge of a black hole, you have this boundary called the event horizon. Pairs of particles and antiparticles just kind of pop into existence right there.
Yeah.
One of them falls into the black hole, but the other one escapes.
Oh,
And it's that escaping particle that we could potentially detect as Hawking radiation.
so even though black holes have this incredible gravity that seems like it pulls everything in,
Right.
they might actually be slowly
Slowly radiating.
radiating energy away like they're evaporating
Kind of, yeah, like evaporating. It's a really slow process, but
over vast stretches of time.
over unimaginable timescales. Yeah.
Yeah, it changes how we think about these objects
Completely changes our perception. Yeah.
as inescapable cosmic traps.
Exactly.
Okay, so we're going from these giant, mysterious objects in space to something much more down to Earth,
Okay.
timekeeping,
All right.
which again, surprisingly, is also governed by quantum physics.
Yes, very much so. And I think it's really fascinating the way that timekeeping has evolved over the centuries.
Yeah, we started with sundials,
Right.
moved on to mechanical clocks.
Yeah, then quartz crystals.
Yeah. But the leap to atomic clocks
Huge leap.
was a game changer.
That was a paradigm shift.
And it's all thanks to quantum physics.
It really is.
So how do atomic clocks work?
Well, they rely on this incredibly consistent behavior of atoms at the quantum level.
Mm-hmm.
So, for example, take the cesium atom.
Okay.
It has a natural resonant frequency, a specific vibration
Okay.
that it makes over 9 billion times every second.
Wow. So instead of a pendulum swinging back and forth, we've got an atom vibrating billions of times per second.
That's a great way to put it. Yeah, and that vibration is so consistent.
Mm-hmm.
That's what makes atomic clocks so unbelievably precise.
And it's not just about having super accurate clocks in a lab.
No, not at all.
This is the technology that makes GPS possible.
That's right.
Wow.
Those satellites orbiting the Earth, they have atomic clocks on board.
Mm.
And it's that pinpoint accuracy
Wow.
that allows them to triangulate your position.
Anywhere on the planet.
Anywhere on the planet.
That's amazing. I never thought of it that way.
It's pretty mind-blowing.
But the documentary mentioned a physicist, Jun Ye,
Oh, yeah.
who's working on even more precise clocks.
Even more precise.
Silphesium ones.
Right. He's working on these optical atomic clocks that are 100,000 times more precise
Wow.
than cesium clocks. He describes it as a quantum pendulum swinging almost 1 billion times a second.
So what can you actually do with a clock that precise?
Whoa.
Besides, being really on time.
Besides never being late, it opens up some pretty wild possibilities.
Okay.
For example, you remember that idea of gravitational time dilation?
Like from the movie Interstellar,
Yeah.
how time moves differently depending on how strong gravity is.
Right. Well, Junior's clocks are sensitive enough
Right.
to actually measure that difference in time flow between different elevations on Earth.
So we can actually
You
see
can see
how time is affected by gravity right
Yeah.
here on Earth,
right here.
not just in some far-off black hole.
Yeah, isn't that wild?
This is blowing my mind, and we're only getting started.
Yeah. We're just scratching the surface here.
Speaking of things that seem like science fiction, let's talk about lasers.
All right, lasers, another great example of quantum physics at work.
Yeah, they're everywhere.
Everywhere you look.
From supermarket scanners to fiber optic cables.
Yep, even in that No VA documentary we're talking about.
Right, exactly.
Yeah.
Okay, so break it down for me. How is a laser different from, say, a light bulb?
Okay, so think of it this way. A light bulb is like a noisy crowd at a rock concert
Okay.
with light waves going in every direction.
Hmm.
A laser, on the other hand, is like a perfectly tuned choir
Okay.
with all the light waves moving in unison.
That's a great analogy.
Thanks.
So how do you get light to act like a choir instead of a mosh pit?
It all comes down to this process called stimulated emission.
Okay.
Basically, when you hit an atom with a photon of light, it can cause that atom to release an identical photon.
Mm-hmm.
And then those two photons can trigger even more emissions, creating this cascade of perfectly matched light waves.
So it's like a chain reaction of photons all moving in sync.
Precisely. And then you put that process inside a chamber with mirrors
Okay.
that reflect the photons back and forth, amplifying them.
Yeah.
And you end up with that incredibly focused beam of light that we call a laser.
I'm starting to see why lasers are so important in so many different areas.
Yeah.
But the documentary also mentioned a physicist using lasers for something pretty incredible.
Oh, yeah.
Right.
Rana Adhikari at Caltech.
Okay.
He's using lasers to measure these incredibly tiny distances,
Like how tiny?
like the ripples in space-time.
Whoa, hold on. So we can actually measure the fabric of the universe rippling?
It's all thanks to this incredible experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory.
Okay.
It's massive. It's got these 2.5-mile long arms
Right.
that use lasers to detect these tiny distortions in space-time.
So we've gone from measuring time with atoms to measuring the very fabric of the universe with lasers.
It's amazing what we can do with these tools.
What's next?
Well, perhaps the most mind-bending concept of all, quantum entanglement.
Okay, entanglement.
Entanglement.
That word always sounds so mysterious.
Yeah, it's got a certain ring to it.
It does. It's as weird as it sounds.
It really is. It's this phenomenon where two particles become linked.
Okay.
Even if they're separated by huge distances, like they act as one no matter how far apart they are.
So if you change something about one particle, the other one changes instantaneously, even if they're miles apart.
Yeah.
That seems impossible.
It even baffled Einstein. He famously called it spooky action at a distance.
Right.
He couldn't reconcile it with his theory of relativity,
Mm-hmm.
which says that nothing can travel faster than light.
So is this just a theoretical idea, or has it actually been proven?
Oh, it's been experimentally confirmed many times over. And what's even crazier is that scientists are starting to harness this spooky action for new technologies.
Like what can you do with entangled particles?
Well, one of the most exciting applications is in the field of quantum computing.
Okay, I've heard of quantum computers.
Yeah.
But to be honest, I don't really understand how they work.
I hear you. It's complicated stuff.
It all sounds very complicated.
It is complex, but the basic idea is that quantum computers use qubits instead of bits.
Okay.
A bit in a regular computer can be either a 0 or a 1,
Right.
but a qubit,
Mm.
thanks to the wonders of quantum mechanics, can be in a superposition,
Okay.
meaning it can be both 0 and 1 at the same time.
Wait, how can something be two things at once?
That's the million-dollar question, right? It's one of those quantum mysteries that kind of defies our everyday intuition.
right.
Think of it like a coin spinning in the air before it lands.
Okay.
It's not heads or tails. It's both until you stop it and measure it.
Okay.
That's kind of like a qubit.
Okay, so a qubit can be both 0 and 1 at the same time.
Right.
But how does that make it more powerful than a regular computer?
Because when you have multiple qubits that are entangled, their computational power grows exponentially.
Okay.
So it's like instead of having a bunch of separate coins flipping, you have them all linked together in some way. The possible combinations become mind-boggling.
Okay, so what kind of problems can quantum computers solve
Yeah.
that regular computers can't?
Well, they're particularly good at tackling problems that involve simulating quantum systems,
Okay.
which are incredibly complex. This could revolutionize fields like medicine and material science,
How so?
allowing us to design new drugs and materials with unprecedented precision.
That sounds amazing. So are quantum computers just for scientists? Will we ever see them in our homes?
It's unlikely that quantum computers will replace our laptops or smartphones anytime soon.
Okay.
They're not meant to be general-purpose computers.
Hmm.
They're more like specialized tools for tackling very specific
So
problems.
we probably won't be playing quantum video games anytime soon.
Probably not, but the potential applications are still incredibly exciting.
Like what?
Imagine being able to develop personalized medicine based on your unique genetic makeup,
Okay.
or creating new energy sources that are both efficient and sustainable.
It sounds like we're on the cusp of a technological revolution.
It really does feel that way.
But are there any downsides to quantum computing?
Well, one of the biggest challenges is building and controlling these systems.
Mm-hmm.
Qubits are incredibly fragile
Okay.
and susceptible to noise and interference from the environment.
So it's not just about building a quantum computer. It's about keeping it stable enough to actually work.
Exactly. It's a huge engineering challenge.
Yeah.
And then there are also ethical considerations to think about.
Like what?
For example, quantum computers could potentially break the encryption methods that we currently use to secure our online data.
That's a bit concerning.
Yeah, it's something we need to be very mindful of as this technology develops.
So what's being done to address these challenges?
A lot of smart people are working on it. Researchers are developing new error correction techniques to make qubits more robust.
Okay.
And there are a lot of conversations happening around the ethical implications of quantum computing.
It's fascinating how quantum physics has gone from this obscure theoretical field to something that has the potential to reshape our world.
It's a really incredible journey.
This whole deep dive has really driven home that point.
It really has. It's a testament to the power of human curiosity and our drive to understand the universe around us. And that understanding, as we've seen, can lead to some truly amazing and unexpected technological advancements.
Absolutely.
Yeah.
But it's also a reminder that we need to approach these advancements thoughtfully and responsibly,
Yeah.
considering not just the potential benefits, but also the potential risks and challenges.
I couldn't agree more. As with any powerful technology, it's crucial to have open and honest conversations about the ethical implications and ensure that these tools are used for the betterment of humanity.
It makes you wonder, what will the next big breakthrough in quantum physics be?
It's hard to even imagine.
And how will it change our lives? It's incredible to think how far we've come with all this,
It really is.
from these early days when quantum physics was this fringe theory
Right.
to now where it's shaping the future of technology.
Yeah, just a century ago, the pioneers of quantum mechanics like Einstein, Bohr, Heisenberg,
Yeah.
they were grappling with ideas that really challenged the very foundation of classical physics.
I can imagine, like, to propose that the
It
universe...
was revolutionary
Yeah.
and, not always well received.
To propose that the universe behaves in such strange and counterintuitive ways.
Yeah.
I bet that was met with a lot of skepticism.
Absolutely. Their theories were radical.
Yeah.
And they sparked some pretty intense debates
Right.
within the scientific community. But these pioneers, they were driven by this unyielding curiosity to understand the true nature of reality. And their perseverance ultimately led to a paradigm shift
Yeah.
in our understanding of the universe.
And that shift continues to this day. It seems like every new discovery in quantum physics opens up even more mysteries and challenges
For sure.
our assumptions about how the world works.
It's true. We're constantly pushing the boundaries of knowledge.
Yeah.
And with every step forward, we encounter new puzzles that make us kind of rethink our place in the cosmos.
It's that sense of wonder,
Yeah.
that insatiable curiosity.
It's humbling
Yeah, it is.
to realize how much we don't know.
It's that insatiable curiosity that I find so captivating about quantum physics. It's like we're peeling back the layers of reality,
Yeah.
revealing this intricate
Yeah.
and often bizarre
Oh, sure.
workings of the universe at its most fundamental level.
And it's not just about understanding the cosmos either.
Right.
Quantum physics also kind of forces us to confront these profound questions about ourselves.
Like what kind of questions?
Questions about the nature of observation, the
Right.
role of consciousness, the very limits of our perception.
It's almost like a journey of self-discovery, guided by the principles of quantum mechanics.
I think that's a beautiful way to put it.
Yeah.
Quantum physics takes us beyond the realm of science and into these realms of philosophy, spirituality, even art. It's a reminder that knowledge is interconnected and that even these seemingly disparate fields can illuminate and enrich each other.
This whole deep dive has been a truly transformative experience, I think.
I agree.
It's left me with a sense of awe and gratitude for the opportunity to explore these mind-blowing concepts.
I share that sentiment. It's been an honor to share this journey of discovery with you,
Likewise.
and I hope it's inspired our listeners to continue exploring the wonders of quantum physics.
Absolutely. And as we wrap up, I want to leave our listeners with this thought. The quantum world is vast, mysterious, and full of untapped potential.
Yeah.
So keep asking questions, keep seeking knowledge, and keep your minds open to the infinite possibilities that lie ahead.
Well said, the journey of discovery never truly ends. There's always something new to learn, something new to wonder about. So until next time, keep exploring the depths of the universe and the depths within yourselves.